what I'm going to do is here, maybe in contrast to the first two speakers, which is really good, is I'm going to look in quite a lot of depth at a concept that we've had for quite a while and we've been developing. I want to start off by recognizing my co-conspirator in this, Jim Angus. So Jim and I have been thinking about this for a couple of years, and recently we put some of the flesh on it, and also we happen to have had a project which complements it. And I'll take you through that in the 15 minutes or so that I've got to talk about this subject. So let me start off with how on earth can an aircraft be conscious? Well, let's look at consciousness. So here's some definitions of consciousness. Actually, all of these people happen to be scientists who've turned into philosophers or futurists. Won't hold that against them. But what you do get into is you get into some very detailed language. The first definition here, you may argue, is intelligence, not consciousness at all. But the second two, there are no typing mistakes, no grammar mistakes. Those are the definitions. So you need to unpack this somehow. And one of my ways of trying to explain this is we don't kind of know what consciousness is, but we in a definition, but we know really what we're talking about. This is an analogy to something like love, for example. We know when we're in love with somebody, we know that what love feels like. But what we can't do is actually define it, put a pin in it. So rather like IVHM and what Ian did before, which was he took some definitions from IVHM and made them applicable to his industry, to his field. What I've done is I've come out with this definition of consciousness as being very like metacognition, the awareness of being aware. Now, okay, so maybe even that's a step too far. So let me unwrap that for you. Let me take you walking down your favorite high street. You're walking down, you see people around you, you see cars in the street, you can smell the smell of coffee maybe. If you're in the UK, it'd be fish and chips as well. But you're aware of what's going on around you. So we've got that. But not only are you aware of what's going on around you, you know you're aware of it. And that's the awareness of awareness. So as a working definition of consciousness, that's what I'm going with. So can an aircraft really be conscious? Given this definition, probably not. But we can start at the right-hand end and work backwards. We can certainly provide it with a lot of the ability to be aware of itself in the first stage. But before I move on to tell you how we framed this project, let's just take a look at the rise of computer power. Now, you can plot this however you like, but whatever it is, it's quite phenomenal. AI, artificial intelligence, you can argue, and a lot of this I'm cutting through. There's a debate to be had on almost every slide and maybe even every topic. People have debated the A in artificial, for example. But this is the progress that we see through the years. The philosophies down at the bottom, starting right at the left-hand side with the Turing test, and going through things like the Chinese room, which is a development on that. Winograd schema, which is to do with how we're ambiguous about some of the things we say and how computers actually interpret them. To today, where we're talking about ethics and do robotic systems, do AI, do they have rights at all? And what on earth do we mean by that? So that's the bottom line. But the curve I'm interested in today is the top one. And as I said, you can choose your own ones. I'm just choosing this to illustrate what I'm talking about. For me, it started with Deep Blue beating Kasparov in chess. And I can't believe that's so long ago, but 1997. It took another 20 years for a computer to beat somebody at Go. So that's 2016. That may be because of the complexity of the game. Chess has got an opening move of 20 moves. Go has got an opening move of 361. And it doesn't really get much simpler for those who have actually played it. Or it may be because the game is simply not as popular as chess. In between those, you see the Jeopardy's come along. The brain projects, both in the UK and the US, have taken different paths. Neural networks are very much in the UK and Europe, concentrating on how those fire, fight and flight, etc. And the Human Brain Project in the US has taken a much broader view. But the two I wanted to get to today are the two on the far right. And I want to talk about GTP3, which actually can produce poetry that's almost unrecognizable from human poetry. And this is where we get into, is it fake or not? So poetry, but the one that came out recently is Google's Loon, which was a high altitude balloon flying from A to B. So what they did is they programmed it with AI and said, okay, follow the path. Well, not follow the path, but get from A to B. And they very much expected it to go through a great arc. And they found it wasn't. It kept on veering off course. So what they did is, as all humans do, they tinkered with it and put it back on course until they realized what it was doing. The AI had actually come up with tracking. So rather like a yacht, you actually run before the wind and then you tack back onto the course you're on, being the quickest way between A and B. It's not directly following the course. This wasn't programmed in the AI. They were very surprised it did this. And you can call it emergent behavior. You can call it what it's like. You can also call it scurry. But anyway, that's what it did. So, okay, we have some of this. How are we going to make this in some way concrete and bring it to a project? Well, the vision that we have in this is very much around maintenance and operation of aircraft. It's in health management. That's what my field is. But it's really, how do we treat the aircraft more like a human? What would we want to see from it? How would we want to do the handshakes with it? And so this is the sort of vision we have here. And to make that, as I say, into concrete, we've gone with this. So these are the elements of the conscious aircraft. So first of all, the aircraft's at the center of this. It has what we think of as a sort of nervous system supplying data into a brain, a computer, somewhere near the flight deck. This is actually probably more applicable to Ian's SHM than it is to individual systems because they need so many more sensors. But all that information is flowing into the flight deck. Now you have to analyze it. And you can do that on the flight deck or you can do that on the ground. And the paths to the ground are marked in blue, whether we're talking about maintenance communication, passengers, whether we're talking about ATM, ground ops, or if we're talking purely about maintenance and the airline and air traffic management. So those are the routes to the ground, those are the blue ones. And those depend very much on comms links and how fast those links are. So whether you process the data on the plane or whether you download it for processing on the ground. But the areas that make up to us the conscious aircraft are those in yellow. So we start off with the top left in operational cost savings. And this is really where IVHM has actually found its way. Can we actually put more intelligence into that to actually decrease the amount of maintenance that we have? In terms of an aircraft operator, can we supply an operator with no surprises? I should also add that, of course, we're doing this for the vehicle. So Nick was looking at this in terms of the engine and then looking at maybe to other systems. We are deliberately looking at it from a vehicle level. We want a self-aware aircraft, top right. That goes with the sensors and actually the information that we're supplying. We've put self-repair in there because we think that's an interesting technology that hasn't actually reached its end yet. Comms with operators and pilots, that's the human handshake we have. And then we go to safety and security, bottom left, which will be enhanced by this. But that's the overall concept. This is an infographic. It's available from Cranfield. It's probably available on the web as well. So now what I want to do is actually look at what that means and how we've taken that forward in an individual project. And I want to just take the intelligence side. We've got the MRO going at the same time, the maintenance, repair and operation. But I just want to take a look at the intelligence side. So what progress have we actually made on this? And what you do in academia is you look around and see what you have. And coincidentally, we've done a PhD that's almost in this field, and that's what we're going to leverage. So what we've been looking at in this PhD is the ability to reason. It's inherently human, but when you come to program it, it's a lot of if then else statements. And I had to put this quote in because actually it's my favorite quotes at the moment. Algorithms are opinion turned into code. I just think that's absolutely brilliant. The book 50-50 as to whether you read it or not, but I just thought that was a really good quote. So our progress has been based around something called FAVOR. This is a framework for aerospace vehicle reasoning. Sorry, I didn't put a name in there, but Cordelia Ezelarazzo did a PhD in this, and this is very much her work. So Cordelia finished her PhD at the end of last year and has since joined as a postdoc. So what it is, it's a framework for exploring reasoning and can be used as a virtual twin, digital twin, whatever you want to call it, to explore the concepts of the conscious aircraft. So what do I mean by this? So this is FAVOR, and if we start at the bottom level, what we see is we see aircraft systems at the bottom, and we've modeled 4 of them so far. So we have digital twins at this level for each of these. the electrical power system on the left, the fuel system, the engine, and the environmental control system. We will add to this and add to the complexity as we go forward, but just for now, we just have 4. And what you see is the interaction between these systems. So the EPS provides electricity, AC or DC, to the fuel system, the engine, and the ECS. That means it interacts with all of these systems. In return, the fuel system provides the engine fuel, and the ECS gets bleed air from the engine, while the engine provides the shaft power to the generator in the EPS. So those are the macro level interactions between these systems. Now, historically, these systems have been diagnosed through stovepipes, and that's what we see here. So as I said, the bottom level is the digital twin. It could be the physical asset as well, but for the moment, let's just consider it to be the digital twin. We then build on that with the number of fault modes that we're going to detect in each of those systems. And then the system diagnostics that are going to detect those faults. So we're totally consistent in each of the columns. What we can't detect, though, is any interacting faults between these systems. And we can't reduce the number of sensors in one system because we can detect something that's gone wrong in that system from another system. So what we do is we form what I call the vehicle system symptom vector at the top from all the sensor data we've connected. And we do reasoning with that vector as to what's going on. And I'm going to give you, hopefully, quite a short explanation of what that's about. So I'm going to start, I'm going to examine an actual accident scenario. This was an Airbus A319, and it was flying along, and one of the engines, the bleed system, failed. Unfortunately, and this does happen, I'm not quite sure why we don't have interlocks for this. The pilots then shut down the bleed system from the good engine, which means the cockpit, the cabin, depressurized because it was getting no air from the environmental control system. So the oxygen masks deployed, there was emergency descent to 11,000 feet, the APU started up, and eventually they stabilized at 15,000 feet. So let's just take this as an accident scenario, that the bleed system failed, and take a look at what possibly could have caused it. Well, the first one is it could have been a mechanical problem. The bleed valve partially stuck open. So again, we have the 4 systems that we're examining, and the green is everything's hunky-dory, everything's working. So the EPS is providing the fuel system with power, the fuel system is providing the engine with fuel, etc. Except that now the bleed valve is stuck, there is the potential for low bleed air pressure in the environmental control system. And this is through a mechanical fault. The second case is that this could actually be electrical. So what could have happened is the bleed valve switch could have stuck open, and that could have caused the problem in the engine, which caused the problem in the ECS. I hope you're with me so far. So which one of these two is it? And do we know how this fault would actually propagate if we ran it forward in time? Well, here are the 2 results from both of those. And what we're trying to do is analyze the current state and then look at how this fault would propagate in time, given what we know about the systems. So on the left-hand side, it's a mechanical problem, right? So on the left-hand column, we have the health states as they come in. We know the engine was at fault because the bleed valve might have stuck in the engine. But what Favor's telling us is, yes, everything's green, but this has the potential to affect the environmental control system, the air conditioning for the cabin. If we propagated that state forward, prognosis, but a very crude one, if you like, we would reach the right-hand side of that, in which the ECS was also at fault. But if the ECS is at fault, it doesn't propagate to any other systems. So the fault that we've seen only propagates to 2 systems if it's a mechanical fault. On the right-hand side, we're considering what happens if it's an electrical fault. And this is a little bit more complicated. Again, we start at the left-hand side. This time we know the electrical power systems because that's what we've said is at fault. And Favor is pointing to the fact that because of that, you could have affected the engine. As we move forward, as we prognose the health state, what we see is the engine going red in the Favor calculation. And it's saying, oh yes, but that could also affect the ECS. So we have to do a further propagation with the ECS, and we end up with 3 out of the 4 systems being affected. So what we're saying is if you left this fault, you'd automatically know whether it was a mechanical or an electrical fault, because you'd have 3 systems down rather than 2 systems down. So anyway, that's by way of illustration of what we're going to use. We're going to use this framework to explore some of the ideas of the AI and the consciousness that I actually spoke about to begin with. So I hope that's going to trip through at least a concept that we've been working, and we look forward to doing more of this in the future. So with that, Toby, back to you. And any questions?